So you're trying to pick a major in tech, right? And it feels like you're staring at this impossible choice: computer science, computer engineering, or electrical engineering. They all sound kind of the same, but they can lead you down totally different paths. Today, we're going to break down this classic dilemma, figure out what makes each one unique, and maybe more importantly, see where those lines are starting to totally blur together.
And let's just dive right in, because this quote from a student forum on Reddit really nails the confusion. People are out there arguing that computer engineering majors, the ones who makes hardware and software, are actually better set up for software jobs than pure CS majors. Is that true? It's a huge debate, and a really important one if you're trying to figure out where you fit in the world of tech.
All right, to really get a handle on this, we got to stop thinking about these as three separate boxes. The best way to look at it is like a spectrum. On one end, you have the pure abstract world of code and algorithms. And way over on the other end, you've got the physical reality of circuits and electricity. The real question is, where on this line do you want to be?
So let's look at the two extremes. On one side, you have computer science. This is the realm of pure software, deep theory, and complex algorithms. It's all about abstraction, basically an extension of mathematics. Then, on the complete opposite end of the spectrum, you've got electrical engineering. This is all about the physical world, circuits, power grids, and the physics of how electricity actually moves. It's the hard science of bending electrons to your will.
And smack dab in the middle of these two worlds, that's where you find computer engineering, or CpE. This is the bridge. Computer engineers are the ultimate translators. They speak both languages, the language of abstract code and the language of physical circuits. They're the ones who design and build systems where the hardware and software have to work together perfectly. And you can literally see this spectrum play out in what you'd study in college. A CS student is going to be deep in algorithms, data structures, and AI. The EE student? They're living in a world of power systems and electromagnetism. But look at the computer engineering curriculum. It's things like computer architecture and embedded systems, classes where you absolutely have to understand how the software commands the hardware, and how the hardware's limits constrain the software. It is the meeting point.
Okay, so if everyone has their lane, what's the big deal? Why is this collaboration so important all of a sudden? Well, it turns out the old way of building things is kind of broken, all because of a huge bottleneck that's been slowing down technology for years.
And that problem has a name: the memory wall. Here's the deal. For decades, our processors got incredibly fast, way faster, year after year. But our ability to feed data to those super fast processors from memory, that didn't keep up. So now we have this massive traffic jam where the most expensive thing a computer does, both in time and energy, isn't the calculation itself. It's just moving data around. And for the longest time, the way we design systems made this traffic jam even worse. This is the old way, the traditional flow. You'd have the hardware team in one building and the software team in another. They'd work in their own little bubbles, design their parts, and then at the very end of the project, they'd kind of just throw it over the wall to each other and hope for the best. You can imagine how well that usually worked out.
But what if, instead of working in separate silos, you just got rid of the wall entirely? That's the idea behind the co-design flow. Here, the hardware and software teams work together from day one. It's a constant back and forth, a collaborative process where every choice is made thinking about the entire system. This shift in thinking isn't just a small tweak, it's a complete game changer. This whole new way of doing things is called hardware-software co-design. And it's not some niche academic idea. It's a pivotal, crucial method for creating the efficient, powerful little computers that are inside basically everything we own now, from our phones to our cars. It's truly a revolution in how we build things.
And it's not just a fuzzy concept of working together. No, it's a very structured process. It all starts with everyone agreeing on what the system needs to do. Then comes the most critical step: partitioning. That's deciding which tasks are better suited for speedy, custom hardware and which can run in more flexible software. After that, everything, design, testing, and final checks, is done together, ensuring the two halves act as one seamless whole. So, all of this collaboration sounds nice, right? But does it actually work? Does it make a real difference? Oh yeah, the numbers are staggering. Let's just look at one case study. Check out this table from a research paper looking at a power management system. Just look at the before and after columns. These aren't just tiny incremental gains. The improvements from applying co-design were massive across the board. First off, a 40% reduction in execution time. That's not just a little faster, that is a huge leap in raw performance.
Next, power consumption dropped by 36%. For anything that runs on a battery, which is pretty much everything these days, that is an absolutely game-changing improvement.
And on top of that, they got a 21% improvement in resource utilization, meaning they were using the hardware more efficiently, getting more bang for their buck. This shows that co-design isn't just a philosophy, it's a powerful performance multiplier.
So, let's bring it all the way back to that first question we asked. CS versus CpE versus EE, which one is the right choice to make?
Well, after looking at all this, you start to realize that's the wrong question. The future of technology isn't about picking one camp. The most exciting, most important breakthroughs aren't happening in those isolated silos anymore. They're happening at the messy, complicated, and amazing intersection where all three of these fields meet.
It's just like the researchers at Harvard said, the only way we're going to solve the really huge problems, like that memory wall, is by designing our data systems and our hardware together. It's about combining the expertise from all these fields to build something better than any one of them could build alone.
So, in the end, the whole debate about which major is best, it kind of misses the point. The most valuable skill you can have going forward is the ability to understand both sides, to be the bridge. Because as we push into crazy new frontiers like AI and quantum computing, the giant leaps won't come from a single field. They'll come from collaboration. And that leaves us with the real question. What's the next great challenge that only this kind of thinking can solve?